on mostly privacy and subsecurity in the area of distributed federated collaborative learning. And we have three main speakers. Adam Smith, no need for an introduction, one of the co-founders or co-inventors of differential privacy and a lot of incredible contributions in the community. Lydia Zakynthinou and Lydia Zakynthinou as well from Google. So they're going to be presenting on a variety of topics. Hopefully we're going to cover a lot of DP, attacks maybe, auditing, memorization, and also some multi-party computation as well. So,
yeah. All right, thanks. So, yeah, hi, I'm Adam. So this is a tutorial that we're put together with Lydia, who's in the audience here. Lydia, who's a faculty member at Johns Hopkins, and Adria, who's at Google. And the tutorial will have like something like 7 parts. I'll talk for a little while about the kind of basic setup and how we model privacy in a bunch of settings. And then Lydia will talk for a while about some of the algorithmic ideas that have been developed over time and what some interesting directions there are. And then we'll come back. I'll sort of finish up with a little bit of discussion about some of the specifics of federated settings and what changes. And then the last part, which is really more than a seventh, it's more like a quarter or something. Adria will talk about some of the cryptographic and other tools that help us distribute these algorithms in sort of federated settings of various flavors. All right. So, general disclaimer about tutorials, and this one in general. This will neither be unbiased, nor fair, nor exhaustive. That's just the way it goes. It's really hard to cover everything, and necessarily there's some perspective that goes into it. That said, I would like it to be informative, so feel free to stop me and ask questions. And I'd much rather get through a little less and have people engaged and talk, following than just talk at you for a long time. It will be kind of theory focused. This is sort of intentional. We're at the Simons Institute, and it's also my own personal bias. But I think also what lends itself well to this kind of tutorial, and really not, this is a program on federated learning, but almost everything we're going to say is really more about sort of aggregate computations in general and not really specific to learning. There's actually very little about privacy that's super specific to machine learning. Although some of the specific problems we'll talk about are kind of learning flavored, but really there's kind of not that many places where learning is the essential part. It's really more about information and how we're kind of aggregating data. And then final disclaimer, I probably forgot to cite your paper. I might have forgotten to cite my paper. Feedback is welcome, but I'm not even going to try to cover everything. So I apologize ahead of time for failing to mention your paper. All right. So we're talking about privacy and machine learning. Really, we're going to look at, this is the classic machine learning pipeline. We've got data drawn from possibly from some underlying population. A learning algorithm produces some output in the form of maybe a model or a classifier that hopefully teaches us something about the underlying population, or at least the data set. But the question is sort of what can we infer? The kind of question that's going to drive most of today is sort of how much can we infer from the learned model about individual records or individual contributions to the training data, and to what extent does that conflict or help us do good machine learning and do good kind of statistical analysis? Notice that privacy can mean lots of things when we're talking about machine learning or anything else, right? Often it's used sort of in a somewhat different, with a very different perspective of thinking about control over how your information is used. And so that's sort of a really interesting set of questions that come with that we won't be talking about today. It's often used, sometimes when we're talking about privacy, we're actually thinking not about individual contributions, but about higher level trends. Okay, Strava is this app Strava is like an exercise app that many of you have heard of. A few years ago, it was realized that Strava's sort of aggregate statistics on running routes were basically detailed maps of US Army bases because, soldiers run a lot, right? That's sort of it's certainly a confidentiality issue. It's sort of a privacy issue. It's not really the one we're going to be focused on today, but it'll kind of pop up in a couple of places from one angle or another, and I'll sort of connect back to that when I can. Okay, but generally these are not going to be our focus. So I'll talk, first part of the talk about sort of like motivation. We'll start with some like what can go wrong. 3 vignettes of theoretical approaches to understanding what can go wrong. And then a little bit about some of the other modes of attack that I don't get to in more detail. But, Okay, no surprise here. Models store detailed data. One of everybody's favorite examples is this paper from 2020 that, took this very large language model, GPT-2, and, poked it, and it just spit out its parts of its training data, right? Similar time frame, people looking at the early diffusion models, or some of them, not the early ones, but the more early successful ones, showed that with, again, with a bit of poking, you could get the models to spit out near perfect copies of some of their training images. Okay. So we know that models store lots of detailed data. This has been explored a lot from the point of view of generalization and just understanding good performance of models, very much from the point of view of interpolation and overfitting. And there is this kind of interesting connection to privacy there that I'll come back to. But generally, this is sort of not the perspective we're going to take. We're going to be looking more at not so much interpolation. This is, for example, the picture on the left is a picture of literal interpolation with a polynomial. Picture on the right is from a paper a few years ago on, quote unquote, rethinking generalization, and specifically on experiments where, deep models that generalize beautifully on real data would also just happily memorize random labels and interpolate through them. But and understanding the difference between these settings is sort of like an interesting question. There's not really the perspective we're going to take, but I'll touch on it a little bit later this morning. And then another kind of example that comes up is just sort of reconstruction of a seemingly more banal variety, where very detailed statistics have been used. For example, people looked at the 2010 census results, and the census itself, the US Census, did a study where they showed that they could reconstruct lots of detailed household and individual level statistics from the supposedly aggregate tables that were published in 2010. Okay, and that drove a complete redo of the confidentiality machinery for the 2020 census, and lots of debate in the community of people who use census data about whether or not this was justified, and so on and so forth. There's a lot to say about that. But I just sort of wanted to kind of, these are just a few striking examples that have been part of the kind of public discussion for the last few years. And then maybe just ask what's the role? What are the roles, or what is the role for theory in this type of discussion? Okay, because all these examples are just that. They are, real examples where people tried things out and they worked. And of course, this sort of general role that we hope theoretical research and understanding takes on is, abstraction on one hand, and principled understanding that ideally generalizes, no pun intended, to other settings. So this comes in a few forms, right? It allows us to, for example, it's important, the theoretical perspective is important and has been important for formulating threat models. It's been important for talking about evaluating attacks and thinking about which attacks are really significant. This is not something I really have time to get into. I'd love to have spent another half an hour on this, but I don't have time, but I'll just poke at it a few times. And then, and this will be kind of my focus today, sort of like its theory is really useful for understanding when attacks are unavoidable. Often, even in very simple, seemingly stylized settings that at least theoreticians view as sort of like obviously embeddable in lots of real-life scenarios. And then, of course, defining criteria that ideally provably prevent attacks, at least attacks of a certain variety. And to some extent, designing methodology in practice to help us what are so-called audits that I'll touch on very, very briefly. But this is certainly a big deal at the big tech companies right now of sort of finding ways to stress test or red team potentially released models to understand what can be extracted from their data. Okay, but somehow my animation got messed up again. Whatever. The sort of unavoidable attacks, the high-level lesson that I want you to kind of remember, and that I think has been the sort of lesson from this literature over the last now going on 20 plus years, 23 years, is that when you release too accurate statistics, even aggregate ones, about a data set, you end up releasing high-level information, like individual-level information. Okay, and back in 2003, we were talking about releasing lots of statistics, but over time, we've sort of, that evolution is, that sort of view has evolved, and it's not really the number of statistics per se. There's something about the inherent dimensionality of these things that seems to really be driving a lot of the problems, but also the success of the approaches in learning. Okay, but maybe the sort of easy corollary of this is that you really can't release everything everyone would want to know about your data set. And so, broadly, what we need we're facing a real trade-off. And what we need are tools to help us navigate that trade-off. Okay, so this talk, this part of the tutorial, I'll go through 3 vignettes, little like examples of theoretical analyses of sort of unavoidable attacks, just to give you a flavor of what's out there and maybe some of the directions that remain to be investigated. So I'll start with the reconstruction attack due to Neuronicium. This is a classic from back in 2003, arguably the paper that kicked off this entire field, at least the part of it that is focused on rigorous foundations. I'll talk about membership inference and in particular a perspective that came out of a paper of Ban, Ullman, Vadan. And then if I have time, I'll talk a little bit about various forms of memorization and a little bit about one paper of mine, but I probably won't have a lot of time for that.
Sorry, Adam?
Yeah.
You'll probably get into it, but it seems that you're separating memorization from reconstruction and membership inference. Is that intentional, or is memorization something different, or?
Yeah, I mean, I think it's more for lack of good words. I'll explain what I mean by memorization as distinct from reconstruction and membership inference. But actually, the short answer is that these things are all closely related. And I decided to do, I was like, actually, as I was preparing this, I was like, oh, well, how can I present these as sort of like in a really nice, clean, unified way? And I decided I wasn't going to pull that off. And so I sort of, backtracked and settled on, I will give 3 examples. But yeah, I think there's surely more to be said about the kind of fundamental connections between these, and I'll try to highlight at least intuitively what the connections are, but sort of a clean mathematical unified framework is not what we have right now, and I suspect it would be maybe unwieldy even if one were to come up with one. So maybe not the most productive approach. Okay, so let me. So this is sort of partly in historical order, but partly but not just. I mean, I think these are sort of really important kind of basic examples that come up a lot, even now. So let's talk about reconstruction attacks. So these are sort of attacks where from the output of the system, which you can think of as maybe a classifier or learned model, or maybe not, you're reconstructing some specific part of the data set with some level of confidence. Okay, so this is meant, maybe you can think of this as an abstraction of the kind of things that go on with like the stable diffusion example, although it's unclear that that's the best model of what's going on with stable diffusion. This is certainly very close to what's going on with like the census reconstruction style attacks. Okay, so Zakynthinou and Nissim's setting looks like this. So they consider this very stylized setting that it turns out you can embed in lots of like more realistic scenarios. But the stylized setting they considered was this. There's some data set, we'll call it X, and it has 1 bit of secret information per person. And this, so think of the like, are you diabetic or not? Pick an example. Okay. And now you've got some algorithm that is going to release what are called linear queries, which are more or less what the name entails. So I've got a bunch of vectors. We can imagine them as vectors in +1, -1 to the n, or 0, 1 to the n, it doesn't really matter, or real vectors. And the thing I want to release is the approximate inner product of each of these vectors with x. Okay, so we want to know how x correlates with a certain set of things. Okay, and so we'll think of this sort of learning algorithm as getting these set of queries is public information. Either it's selected by someone outside the system, or maybe it's selected by the learning algorithm. But whatever, it's presented as public. It's not. There's no kind of obfuscation of that information. And then it takes this sort of secret data set and it produces an approximation, which I can think of it as an approximate matrix product, but an approximation to each of these inner products. And let's say that we get some accuracy guarantee, like each of these inner products is accurate to plus or minus alpha n, where alpha is some parameter. N is the number of people, so n is the range of the query. The answer to the query is somewhere between like -2n and -n and n, right? So alpha is sort of the relative accuracy of the answer, and let's say it's accurate for 99% of the queries. And so this kind of setting captures a bunch of things. Well, it captures query systems which exist where there's a sensitive data set and an analyst can formulate queries, can like ask questions to the system. And it also captures any setting where you're getting some kind of correlation between a secret data vector and, for example, a set of other features that are public. Okay, so something comes up in learning, for example, or settings where you could imagine a data set where only the labels are sensitive and the features, the training features are public information. This, for example, comes up in advertising settings because of the features are information that's already available to everyone in the system, roughly speaking. And there's this, actually, if you don't believe me that this sort of stylized setting actually captures real things, there's this nice paper of Cohen and Nissim from a few years ago that looks at attacks on some specific system called diffix that uses exactly this sort of perspective. Okay, so the theorem, due to Zakynthinou and Nissim, and subsequently refined in a few by other papers, is that if I have a linear number of queries, if I have as many queries as there are people in the data set, or people in the part of the data set that I'm attacking, and I have this accuracy guarantee that all of the queries are accurate to within alpha, then there's a way to reconstruct, given the queries and the vector of answers, I can reconstruct a vector x prime that is close to x. And how close? Well, it's going to agree with x on a large fraction of x's entries, on almost all of x's entries, as long as this quantity alpha squared n is small. Yeah?
Two questions, just in a second. What's the quantifier over the queries here? Is this, there exists some set of queries? Or
Yeah, that's all right.
Queries?
Yeah, that's a good question. So I could say, so that was a good question, Nati. I should have. There are several answers to the types of queries that allow this. But for example, like random uniform in plus minus 1 to the n or 0, 1 to the n will work. And as well as various like sort of structured sets of queries. So anything with structured sets, with structured queries generally requires harder math. With the one exception, there's like a nice paper by Dwork and Yochanan where they look at queries that are the rows of a Hadamard matrix, and then it's really easy.
But just being in general position is not sufficient.
No. So good, yeah. So let me finish the statement, and then I'll just say.
Question related to this. So when you say k equals O of n, can you do it with any linear fraction? Can you do it with k
let me finish stating the thing, and then I'll take. So the number of queries it takes depends on exactly how they're selected, but if they're random queries, then there is some constant, let's say 4 or 5 I think is sufficient, such that if I have like 5n queries, and the accuracy of these queries is alpha, then I reconstruct a 1 minus alpha squared n fraction. So what that means in particular is if alpha is less than 1 over square root of n, meaning if I'm kind of getting relative accuracy that is like higher, roughly speaking, than random sampling, if you want a calibration point, then in this kind of worst case sense, given the queries and any accurate answer vector, then I can actually reconstruct this x prime. And like as an intuition point, maybe start with Nati's question about like, is general position sufficient? So suppose alpha were 0 and I were getting exact query answers, right? Then I would be getting, I'd be getting some linear transformation applied to x exactly. And I could reconstruct x exactly if and only if the matrix Q is invertible. Okay? So mathematically what's going on here once you add error is you're looking at various robust types of robust solutions to systems of linear equations. And these entail other mathematical properties of this matrix that are not just invertibility, things like bounded singular values, or this what's sometimes called the restricted isoparametric inequality, the sort of math related to stuff that comes up like that. If you're those of you old enough to remember when that was like a thing people in machine learning studied. So these are the kinds of properties of this linear system that come up, and I'd be happy to like talk to you all. I'm not going to spend more time on it than this, but I'm happy to talk offline about it. But like maybe the simplest type of analysis along these lines, that non-trivial analysis along these lines, looks at the singular values of this matrix, and basically as long as it is not merely invertible but kind of has no small eigenvalues, then you can tolerate a certain amount of error. Okay, so this is like one flavor of result that comes up that says if you get these like super accurate answers to many queries, then you can reconstruct the data exactly. But the strength of this result is also one of its limitations, in the sense that notice that the statement of this theorem says for any answer vector that is sufficiently accurate, it doesn't say anything about the way this vector was produced. Okay? And so that's a very strong statement, but it also, because there's sort of no, We're not making any distributional assumptions on the data or anything like that. And that means that you can't really produce a stronger statement than this one if you want, let's say, a polynomial number of queries, unless the number of queries is, say, exponential in the size of the data set. So this was one of the first results, but this definitely got people's attention because it's sort of like, it was maybe the first really crisp formalization of this idea that you have to be, that you can't get sort of privacy for free. Yeah, Mehdi.
So, like, my question is, can you have a better guarantee? I'm saying that, let's say you reconstruct an X hat.
Yeah.
Can you, for example, say that I'm pretty sure this subset of bits are exactly X, but I have no idea about the rest?
The question was, can you get like higher confidence about some of the bits,
But yeah.
say? In general, no. So like one of the ways you could produce this output with an accuracy guarantee along these lines is you could, what the learning algorithm could do is first flip each bit of X with some particular probability and then answer correctly, exactly answer the queries, but on this vector of flipped bits, some of which are flipped, right? And that'll give you this type of accuracy guarantee where the parameters depend on the probability with which you flip the bits. But it won't. But there you can't. An attacker, an outside attacker, can't have any significant confidence about any of the individual bits of X. So the sort of yeah. In general, no. But maybe there are settings where it's like yes. Okay. So that was sort of my first example that I wanted to give. The second example is going to kind of take a much more statistical perspective, but allow us to prove stronger statements. Okay, and this example, so as I said, this is sort of like the second example looking at membership inference attacks. So membership inference attacks are attacks that have the following flavor. So I've got some population that I'll think of as sort of large and like from which a population from which I could draw samples. And now I've got a data set that's drawn from this population and a learning algorithm that does something with the data set and produces hopefully useful answers, a useful model or something. And then along comes an attack. And the attacker is given either a random member of the data set or a fresh sample from the underlying population. Okay? So the attacker is given a target data record, and the attacker doesn't know if the target data record is in the data set or out. But the attacker wants to infer this based on, so the attacker is going to get the target, it's going to get the output of the learning algorithm, and then it's going to try and guess in or out. Okay. And it turns out this class of attacks has played a really outsized role, maybe not outsized, but a really crucial role in our understanding of the kind of problems that can come up with privacy. Like on one hand, it's a very strong attack model because the attacker is getting the entire record of somebody who may or may not be in the data set. Okay. Often you don't really need the entire record, you just need like a big chunk of the record, but we're not going to like fight over this particular distinction. The other thing that makes the attacker strong here is that there's a very clean statistical model for what's going on, right? The target is either a random member of the data set or a random member of the underlying population, and furthermore, the underlying population is where the data comes from. Okay, so on one hand, a strong setting. On the other hand, like not an unreasonable one. And there are certainly lots of settings where membership in the data itself is sensitive. You can think of it like a clinical trial or something. But these membership inference attacks are often also used, they're also sort of used because there's this kind of feeling that if you can pull off a membership inference attack, you're probably revealing something interesting about these individual records. And maybe you can convert that into a stronger type of attack. But then another nice feature of these things is they come for free with an evaluation setup, right? Because you need to evaluate whether or not the success of an algorithm. Here's your experimental pipeline right here. You write down a population, you sample in exactly this way, you run the attack, you get in or out, you ask if it's correct. And so this gives you like right away a kind of a clean empirical framework for testing things. And that, it turns out, is really useful, as we know, for developing methodology. All right. Sorry. So this flavor of attack actually dates back to 2008. There was this paper that came out of the genetics community looking at what you can remember what came to be called membership inference attacks. They didn't call them that at the time. They called them tracing attacks. Well, they didn't even call them attacks, but whatever. They were looking at what you can do with exact high-dimensional summaries, and they were specifically looking at genomic data. And they had like a sort of a dual perspective on it. One, they were thinking about privacy, but they were also thinking about this interesting forensic problem of like what happens if you get, to be kind of grim about it, a pool of blood with several people's blood in it, the blood of several people. And now what you can do is like look at sort of features of the pool of genomes that are in this blood, but you don't have experimentally a way to tease them apart. At least we didn't. Like at the time, it was hard to do so. And so you get all you get are sort of aggregate statistics on what fraction of the people whose blood is in the pool have a particular genetic feature, like a particular mutation in a given position of the genome, things like that. This was formalized later starting with this beautiful paper of Ban-Alman Vadan, and then there's a whole lineup of other follow-up papers, some of which I was involved in, giving more robust versions of these attacks. So these are distorted high-dimensional summaries that allow an attacker to test membership in the data set, and I'll give you a little flavor of that. And then a few years later, inspired by these papers, there was this paper of Chokri, Stranati, Song, and Shmadikov that looked at applying this type of attack setting, but in this emerging kind of exciting world of machine learning at the time. Machine learning like as a service where the training data is hidden and the model is on the cloud, and I can kind of query the model. That was like a brand new thing at the time. And so what they pointed out was that was actually a great setting for these membership inference attacks. And that there's our like interesting methodological approaches. Like none of the kind of algorithmic ideas per se in this paper are used anymore. People have kind of moved quite a bit past those. But the framing of the question was first made there. And then there's just like lots of other stuff here that I'm not even going to try to survey. But there's certainly like lots of nice work on membership inference attacks in practice, both on sort of more kind of traditional statistical settings and ML ones. Sorry, yes, Adria.
So I can make sense of this, the empirical version of this definition.
Mm-hmm.
If the data set is known to the attacker. But how does it work in the last setting? Like, if the data set is sort of known to the attacker, it's known to everyone, you're going to secretly subsample from it and then measure advantage. With respect to that secret sample, this makes sense to me as the empirical version of this, and you're sort of, the public data set kind of plays the role of the population, right? Of the population.
Yeah, so like what's this population, right? So you're saying in a typical experimental setup, the population is some like public data set or some data set, whether or not it's public, it's made public. But some data set from which the attacker can also sample. So I think the view that the SSSS paper took, and that I think is a reasonable one, is to think of the population as just like a real people out in the real world. And so if I tell you this model was trained on personal photographs uploaded to Flickr, then what I can do to sort of, in order to like evaluate my attack or to try and run the attack, I can go and find other photographs that are presumably similarly distributed to the ones on Flickr, uploaded to Flickr, right? I can go use the ones that were uploaded to Google Photos or SmugMug or whatever. Okay. Maybe we'll come back to this if we have time, but yeah. So this, it's sort of in a clean experimental setup, I have complete control of all the bits and pieces. Like when Google runs an audit, that's what's going on. But it sort of actually the setting that was considered in this paper, you don't necessarily have full control of this. But what you can do is you imagine that or assume that you know the kind of data it was trained on, and then you might have access to similar data.
So that's where I'm a bit confused, because an attacker, I'm worried about sort of vacuous attackers, like something that may look like an attack that is not such thing, because I'm just finding photos that look similar to the ones you might have used. But,
right.
Just because I happen to know.
Good. So like definitely when you're evaluating, okay, there's sort of two questions here. One is, how do you evaluate, to what extent should the attacker be confident or not confident about their judgment on this, on this sort of membership bit, okay? And that is definitely tied to how good their like understanding of the population is, for sure. So the sort of confidence assessment you make is only as good as your statistical modeling of the true data. That's sort of unavoidable here. And then in terms of like, how people write papers and sort of announce that they've broken such and such, you also have to be careful, and of course it's easy to screw up. So the way I've presented it, there's only one population. We know it was the source of the data set and the target when the target is not from the data set itself. The extent to which these attacks survive modification of that assumption will vary on how severe the modification is. Yeah?
This is somewhat related, but I think a bit different. So I'm curious, maybe it boils down to parameters here. What does this, in the typical setting, the parameters here, does this mean I can find a constant number of, a constant fraction of the people in the database? Or does it mean if I can find one of the people in the database? Does that rest in population being small? Like what, does that like, or does that for any person that I randomly draw, can I reliably tell if they're in the database or not? What's the kind of type of thing I can do?
So the question is like, what should be, okay, so let's start for a few things. Well, think of the population as really big.
As infinite. Okay.
Sure.
So in that case, I can't actually find anybody in the database, just by being able to do this. Okay.
Well,
I mean, if I have black box access to this attack, this I don't see how this allows me to find somebody in the database.
No, it doesn't allow me. Yeah. So I think I understand what you're saying. You're saying like, what could I use this to do like exhaustive search over the population?
But if it's infinite, I can't.
Right. So the basic setting is, imagine that I already know a lot about I know a lot about someone, and I will try to determine whether or not they are in the data set.
Right. And
this is going to be, relevant when most relevant when the prior probability of them being in the data set is not 0.
I understand.
Right.
So this it allows me to do, right? I mean, but it doesn't actually allow me to reconstruct the database.
No.
To find anybody, to identify.
No. Yeah. I'll come back to that at the very end, but yeah, this is not a reconstruction attack. This is a much on one level, much weaker attack because of the sort of statistical assumptions here, and because of the fact that I'm kind of assuming that I'm getting a data point which is either like in the data set or not, and it depends with how, but typically like my confidence in this judgment might be 95, 99% optimistically. It's not going to be, typically not going to be like 1 in a million or 1 in a billion or whatever it would take to kind of exhaustively search the population. Does that make sense?
Yep.
Yeah. So these attacks, maybe just to follow up on that. So these attacks are often used as sort of like a worst case kind of almost worst case kind of attack, in the sense that like they're trying to hand the attacker as a fairly strong advantage in terms of understanding the background information, but not more than that. Like notice that like what the attacker knows about the data is just that it comes from the population.
But it's that if I do reconstruction, non-trivial reconstruction, I can't necessarily do this attack. I mean, it's incomparable.
It depends reconstruction of what. You know what? I'll come back to. Let me talk about it in like 6 or slides or so. Okay, so here's this is a theory talk. So here's a basic theoretical setting where we can actually like make this work. Okay, so we've got some population, and the elements of the population are binary feature vectors. Okay, so for each person, I have d binary attributes that are either 0 or 1. I have n people. The kind of motivating assumption that was the motivating scenario was in this one of the motivating scenarios in this paper of Homer et al. Was genome-wide association studies. So there D might be in the millions. So these are like positions on the genome that commonly vary among humans. And a typical setting n would be less than 2,000. So like big D, smallish n. Okay, so this is our setting, and now we've got, the kind of statistic we want to know is just the average, the frequency of each of these binary features in the data set. Or actually, the thing we're really interested in is maybe even the underlying population, but in the data set. And what we're going to assume, so in the original version of this, that the attacker was given these exact averages, these exact binary averages, so now the averages are between 0 and 1, and is handed the data of someone, let's say Alice, and Alice is either a random member of the data set or a random member of the population. And what they showed, and this was sort of like, well, Homer and I did some analysis. This was sort of nicely formalized in a paper of Sankararaman and others. We're going to talk about that in a second. So give me a second, I'll set that up a little more formally. But under sort of, let's say for IID data, where in the original setup, all the the true population mean in each column is bounded away from 0 or 1. So there's some variability in the data. Then this attacker will succeed with high probability when there are more attributes than people, when D is bigger than N. Okay, and in fact, their sort of confidence will, the probability that they're wrong will go down as some exponential in D over N. So as D over N gets big, their confidence increases. So this was the basic result. But there's also a more robust version, and this is sort of the perspective that came along with BUV, where now I'm going to allow a process that tries to provide some kind of confidentiality. So you're allowed to mess with each of these. I've got an algorithm that's allowed to mess with each of these averages up to some accuracy alpha. Okay, and the result is that, and now we're going to release, instead of the exact column averages, these distorted column averages. And the result is that the attacker succeeds with high probability as long as there are more attributes than people, so that's sort of D bigger than N. And the accuracy of the answers is now less than about square root of D over N. Okay? And so, and this is sort of true no matter how the distortion was performed, as long as the algorithm performing the distortion sees only the data. Okay? So it's not allowed to go and get more samples from the underlying population. That's cheating. Because if it were allowed to do that, it could just ignore the data and go get samples from the underlying population, right? So, so why is this sort of? So this threshold is this quantity is significant for reasons I'll get to later, but just for now, notice that one of the sort of striking things is it changes very quickly with the dimension, right? So the higher the dimensionality of the release, the more error the algorithm can tolerate. And this saturates at like 1 because the alpha bigger than 1 doesn't make sense here, but I didn't write max of blah, blah, blah. But, but basically, as long once the dimensionality is large relative to the size of the data set or the part of the data set that you're actually interested in, if you can narrow things down to like a part of the data set, the part of the data set you're trying to attack, so now that this attack is much more robust. And I should say that these attacks have been generalized to, so I'm phrasing everything in terms of binary estimation because it's simple, but these attacks can be sort of ported to lots of other settings. So, Gaussian mean estimation, stochastic convex optimization, linear regression, lots of sort of clean statistical settings, or almost any clean statistical setting you want to write down, you can sort of embed this type of example in that setting. Okay. And so maybe for calibration, if I didn't care about privacy, I could give you what the algorithm could do. The exact column averages are going to be representative of the population up to plus or minus, call it 1 over square root of n. And that's below that region is where these sort of reconstruction attacks that we mentioned earlier work. And now these sort of more robust membership inference attacks, they work in a kind of potentially much larger range, or at least this number is bigger than that number over there exactly when D is bigger than N. Okay, so the purple region is sort of non-empty exactly when we're in these kind of high dimensional settings. But potentially, this could be like, if D is really big, this could completely preclude useful answers. Right? Of course, so it's a question mark. It depends on D and N. But yeah. So let me say one more thing. And so that, maybe the lesson I guess I want to draw. I'm saying just hold a sec for the question.
Why the question mark?
Oh, well, because whether or not one lives here or out there depends on D and N.
Oh, okay. There's no question if D is bigger than N squared, then
yeah.
This, okay.
Yeah. So like, if D is bigger than N squared, then then one lives here. Otherwise, one lives in a different place on the plot.
Hidden assumptions here or something.
No. Sorry. This is probably more confusing than it is helpful.
Sorry. It's just me that's confused.
No. I mean, it's a good point. I guess the main point I wanted to make is that potential, like this sort of original reconstruction attack doesn't rule out any non-trivial answer. It only rules out really accurate answers. But these membership inference attacks can rule out like any non-trivial accuracy. And so the lesson I want to draw, again, too many too accurate statistics start to reveal individual data. And also, like, what goes with that is that sort of the idea of what is exactly aggregate is a little hard to pin down. So each of these statistics individually seems really uninformative, but taken jointly, there's a lot being encoded because of the kind of high dimensional nature of where we are. Okay, questions? Yes, I've forgotten your. I don't actually know your name. Yeah. Okay. Yeah.
So are these thresholds sufficient, or they're also necessary? Like, can things go down?
Yeah, so we'll talk about that. I'll get to that in a sec, but it turns out there are differentially private algorithms whose accuracy lives like here. And so if you there are like, you can provably avoid these types of attacks if you're willing to give accuracy that's out in this region. So this bound is tight.
How do I think of accuracy in the second model? In the first model, I understand that alpha relates to accuracy. In the second model, how is alpha related?
So how is alpha related to accuracy? So either I can ask for, typically we'll ask for accuracy just relative to the underlying population. But you can also ask for accuracy just like you can just ask, I want to give you the empirical statistics as accurately as possible. And then
in each coordinate?
Coordinate by coordinate. Sorry, what does this alpha mean? It means that coordinate by coordinate you have a guarantee on the accuracy of the statistic. Of the released value, that the released value is close to the true column mean individually for each coordinate.
I guess my question was the opposite. So above, for a higher alpha, so I understand you're saying something, but for a lower alpha, can I design an attack, either reconstruction or membership inference, which would work? Because you showed in the first thing that there's this result that for k up to k big O n, there are either these random attacks or structured attacks which work. Is there a low bound which shows that no other attack exists if alpha is like
Reconstruction attack exists above 1/√n?
Yeah. So these reconstruction attacks, they work. Like what's pictured here is the region in which the attack works. So these reconstruction attacks along the lines of de Nurnesium, they work up to some accuracy 1/√n.
For any release, right?
For any release that, I mean, the way I define the problems, they're not quite the same. So it's like a little tricky, but yeah, let's pretend that this comparison makes sense. And then here, if you go past that, the reconstruction style attacks can't work. That's provable.
So that's what I.
But these robust membership inference attacks can nevertheless work. So
I mean, in the regime d square, okay, but you're saying they can work beyond 1/√n or even beyond square root d over.
So the point is that like this number here. So this is the limit at which the membership inference attacks stop working.
So
right?
probably they stop working.
They provably stop working. They provably work up to that point and not past it. Yes.
Okay.
And furthermore, that notice that square root of d over n is bigger than 1/√n if and only if, let's just make sure we're getting the math right, d is greater than n. Yeah.
I had one more question, but if others have.
No, it's good. Questions are good. Like it's better to go slow and actually take questions. And
the membership inference attack,
Yeah.
you give me analysis row,
Yeah.
and then I have to say yes or no.
Yeah.
Does this threshold change if I don't get the exact row? I get like some information about the row, and then I still need to run the attack.
Good. Yeah. So you can. It sort of depends. You can. It depends on the kind of information. So you can definitely run the attack with a subset of the coordinates if that subset is big enough. So that becomes your new D, basically. If you're getting a noisy version of the target, for example, then it'll depend on your exact noise model. So there'll be some limit up to which it will, beyond which it will not work. I can't do the math in my head, but my guess is that it would sort of work up to the point where, like, you're much closer than a random member of the population would be to one of the rows of the data set. Like, that's the region in which the attacks would work. Yes, Adria.
Yeah, I think it's related. Can you go to the slide, the previous slide? Yeah. So what's the role of the population here? For example, say that distribution is such that there's only one possible data point that you may ever see. That sounds like a hard situation.
Yeah, so I was going to define I'll actually going to sort of give a proof sketch, and I was going to like define the population exactly
For which this is true.
for which this statement holds. Yeah, but I'll try and answer your question without that. So what's the role of the population? So these attacks rely on the algorithm that processes the data. As I said, it shouldn't have access, it shouldn't know the population, because if it knew the population, it wouldn't even need the data, right? So for example, if the population is degenerate and there's like really just one possible person in the world, there's only one person in the world, and every time you sample, you get that person over and over and over again, then these attacks will fail. The way they're typically analyzed is assuming that the columns are independent, and furthermore, that the true column mean is unknown to the algorithm. There's like the population mean is unknown to the algorithm. If the algorithm knows the population mean, it can just ignore the data and publish the population mean, and it'll be fine. Then obviously, there's no attack that's going to work.
And does the attacker? I wasn't sure whether Alice's data is picked by the attacker or.
So we're comparing two settings. Either Alice is a random member of the data set, like a random row of the data set, or Alice is a fresh sample from the same population. So those are the two kind of conditions that the attacker is trying to distinguish between.
So an attacker could be very good at outliers, right? So it would make sense maybe to restrict this setting to some conditioning on the distribution that the attacker likes.
Yeah, that's true. So this comes back to sort of like an earlier question about like, well, what, maybe from Nati, about like what's the type of sort of success statistic of the, like what's the type of sort of false positive, false negative rate that is interesting here, right? And maybe to kind of say something just briefly about that, sort of typical ROC curve where, right? So we're distinguishing two settings, and so we're, one way to think about the success of the attack is the kind of ROC curve achieved by a given attack, right? And we'll sort of talk more about that earlier, but really, these attacks are kind of interesting when the false positive rate is low, right? So sort of this region of the plot is kind of the most interesting one. And a really successful attack lives way up here, but even an attack that lives here is doing something interesting because it's like correctly identifying, let's say 5% of the points in the data set, but the chances when you handle a random member of the population, the chances that it says yes are going to be, 0.01% or something. Right? Let's pretend that this is the point, 0.01, 0. Or 0.01, 0.05 or something like that. Right? This is an interesting attack because my true positive rate is so much higher, even though it's not very high, it's way higher than my false positive rate. Right? So normally when people evaluate these attacks empirically, if they're competent, they plot out this thing and then look at this corner of the plot. As opposed to saying, well, we got, up here, which is like maybe not that interesting. Yeah.
I mean, what to me complicates a bit this distinction is what is the randomness over, or rather like what is the dependency structure over? Because when you say the probability of something for the same record, if there's some records in which I'll consistently be able to find, or is it every time I have a record outside?
Yeah, so I wasn't planning to get into this. Yeah, you can sort of break things down in lots of ways, and people have. So you can definitely do things like try to come up with a record by record measure of confidence in your judgment. As an attacker, if you've got sort of sample access to the population, you might be able to do that, and if you know the algorithm that was being used. The other thing I should mention that is the kind of, you know what, let me give you sort of like a quick sketch of what's going on, and then mathematically, because I think it'll help answer this question in a second. So I'll go through this fast because I'm out of time, but the population in the theorem I explained, right? The setup is that the population is the population needs to be unknown to the algorithm, right? And so one simple way to set this up is I'll just choose each of the underlying probability of zeros and ones for each column. I'll choose those uniformly between 0 and 1, okay, independently. And now my data set, this sort of, once I choose these p's, these little p's, that gives me a distribution on 0, 1 to the d. And that's my population. Okay. And now what the attacker does is, one version of the attack that works well is, so the mechanism produces some answers, A, right? And what the attacker does, and given a target, the attacker will somehow first estimate this P. The attacker has to estimate P itself using separate data.
But the attacker doesn't know the population.
So either you can assume the attacker knows P, which is the easiest thing, or you can assume it can take fresh samples from the population. Okay, this kind of comes to the looking on SmugMug for photos from the kind that show up on Flickr. And what I'll look is, how does the target differ from the population versus how do the answers differ from the population? And I'll look at how those two difference vectors are correlated. And the idea is that when Alice is just a random member of the population, we can understand this distribution very well. So it turns out it's like really, it's a mean zero. It's more or less normal central limit style. And it has a standard deviation that you can compute that's about, if alpha is not too small, it's something like, the standard deviation is something like, alpha squared of d. On the other hand, if when I take a random member of the population, then what we can show is that the way you think about it is you condition on the data that the algorithm sees. And now, conditioned on the data and the target, and conditioned on the actual data set, this part has almost no randomness left in it. This part has no randomness left in it. And what's random is the true population parameters. They're not very random because you're conditioning on a data set that has n samples per column, so you've got a lot of information about the column bases. But there's enough randomness left in those population parameters that the expectation of this test statistic now is going to be quite large. It's going to be about d over n. And so let's see if I got the math right. That means you've got the statistic for when the distribution you get when someone is in the data set has a mean that is off to the right. So it means some component of the distribution is far off to the right. And so those are people you will identify with high probability. Those are the people your test will label as in the data set. Now this is just an expectation bound. OK, we can get into a finer analysis. I wasn't going to. But this is sort of like just a flavor of what's going on. And so this is certainly the easiest proof to write down for this setting. OK, so this gives you a sense of what's going on is that because the algorithm that's processing the data doesn't actually know the underlying population, basically what we're showing is that there's no way for it to produce reasonably accurate estimates without heavily using the data it got. And so it will reveal information about that data that the sort of estimates it produces will be correlated to the true population parameters in a way that is sort of similar to a random member from the data set. Whereas, like you can sort of, if Z is a random member of the data set, then this term here, what we're really dealing with is something like, the data set average. How does the data set average correlate with the produced answers? And basically, it's impossible to produce answers that are not correlated with the population in the way your data set is. And this is true, it's easy to analyze in this mean estimation setting, but turns out it comes up in, when you're training big models also. This also gets at your earlier question about like, well, what am I conditioning on? So this is, we're definitely using the fact that the population is unknown. And so this is very nice when everything is, sort of like distributed in this nice product distribution, and like things are concentrated in nice ways and stuff. Of course, in real life, it's messier. And so people have sort of looked at methodology for coming up with more kind of target by target measures of confidence, which I don't have slides on, but I can tell you more about offline. Yeah, I feel like I've spent a lot of time here, which is fine. I don't want to like cut off as long as you're interested, it's fine. Yeah.
Seems like it's a conservative choice.
Yeah, this assumption of independence, mostly it helps the analysis. The assumption of independence, like across columns, it's mostly just telling us that, like, what it tells you is that every new column gives the attacker new information, right? If the columns were all the same, then you wouldn't, the attack wouldn't work, right? So you don't really need okay, I don't know what is sort of easy to prove, but like intuitively, you don't really need independence per se. What you need is that every column is giving new, fresh information.
Yeah, my question, I guess, was if you drop this assumption, whether the threshold moves to the left or to the right. But it sounds like.
It depends how you drop the assumption.
Yeah, I guess.
Right. Yeah, so it's certainly, mathematically it's much easier to understand when things are independent. I think it's at some point, there's actually a really interesting general question of like, at what point do you stop trying to generalize the models to make them more and more encompassing of real life, right? So there is a point of diminishing returns where the mathematical complexity goes up, but the insight you get doesn't, right? So I think in my mind, this model like definitely lives in the setting where like it is useful and insightful and relatively simple to think about. But yeah, you can sort of try to generalize, at some point generalizing the model too much, you might as well just run experiments, which is what lots of people do. Yeah?
How do we generalize this analysis to, you mentioned like stochastic complex optimization or, I know that this is like mean estimation, so it's a very important component of training or learning.
Right. Yeah, so okay, the question is how do you generalize this? So let me first say like we don't need to limit ourselves to binary data. I could have exactly the same slide with everything Gaussian would have worked. And in fact, the same proof strategy works. You can sort of write down these distributions. Everything's very clean. That's the version I teach when I teach it in the class. Because the conditional distributions are a little easier to figure out in the Gaussian setting. once you embed, okay, so there's sort of a couple of settings and ways you can embed this in terms of like more kind of learning-y problems.
Just iterative methods or something.
Right, so one way to think about it is like, well, you know, what is a first order optimization method doing? It is doing like mean estimation at every step, right? So that's certainly one reason to think about this as relevant. But also, you know, another kind of trivial answer is like, well, if your loss functions are linear and you're optimizing over the unit ball, then it turns out the you know, optimum solution to your stochastic convex programming problem is the vector of population means. And so, you know, if you're solving convex SCO, you're solving mean estimation. So there are sort of various ways in, like sort of reductions in the standard CS version of the statement where you can reduce from mean estimation to stochastic convex optimization. I think I got the direction right. And this is, you know, and so this sort of is one answer to your question. But the other answer to your question, I think, is maybe more interesting, which is, and maybe I'll come back. The other answer to your question, to some extent, we don't know. Like there are certainly sort of statistical and learning settings where it's not clear what the right mapping is, and finding like understanding membership inference attacks that are kind of native, for lack of a better term, to the model would be useful. And we have some handle on that, but it's very limited. Okay, so maybe I'll just be, oh man. Let me wrap up this part of the talk because like it's coffee break time. Okay, membership inference attacks, one way to think of them is lower bounds. That was the original motivation for Bunnelm and Vadan. It's not, you know, generally not the way membership inference attacks are thought of, say, in industry. They're more used as, they are often used as sort of auditing methods, where auditing here shouldn't be taken in the sense of like the way you know, a CPA does an audit, where it's like if you pass the audit, you're certifiably okay. This is more the other way around. These are, when we say audit, the way auditing is used in this context, these are sort of red team style methods that are used to poke at a particular system and try and find problems. Okay, so they are attacks that are used as diagnostics. Okay. But there are also lower bounds on the accuracy, say, of differentially private learning, for example. They can also be used as reconstruction attacks. This gets to Nati's question. Imagine I have like a data set of size 2n that's known to an attacker, and some half of that is in, and some half, the true data set is sort of in or out, and I can like imagine an extra label, which is 1 for the people who are in and 0 who are the people who are out. In some sense, a membership inference attack is reconstructing this last column up to some accuracy. And that perspective is okay, I don't want to spend time on it. That perspective is sometimes useful as you kind of look into the, you know, think about which type of attack makes sense for a given setting. But of course, this is sort of a weird, in general, it's kind of a weird setting that I'd have like data sets that I, you know, half the data points are in, half the data points are out. But like one place where this does show up is, say, I might imagine a clinical study where I know who's in the study, but I don't know who has the disease that's being studied. If statistics are published separately for the cases and the controls in the study, which is actually very common, then we're really in the setting where the membership inference and reconstruction kind of are the same thing. Okay, so lots to be said about open directions. In general, you know, understanding more general settings. There's a lovely paper called the Score Attack paper by Tsai, Wang, and Zhang that kind of tries to do this kind of thing, and for like kind of traditional parametric models. there's a set of papers, starting with this paper of Steinke and Ullman, on selection problems. So these are problems where I'm optimizing over a discrete set rather than publishing summary statistics. And they have a similar kind of mathematical underlying foundation, but the kind of techniques end up looking different. I won't say more than that. Maybe I'll just say that, like, in general, the sort of settings we understand often are still a little disconnected from the sort of large-scale learning that we are, these days most excited by. Partly because the population isn't well defined and various things. Mehdi, John, and I have a recent paper that tries to get at some of these questions that I'm not going to talk about other than mentioning its existence. I was going to talk about some work on sort of information theory and memorization and its connections to generalization. I don't have time. Sorry. OK. There are lots of other things people do to attack machine learning models, not just sort of membership inference attacks. There's sort of other modes of attack that are problematic. You can think about data poisoning, where you're messing with the data set. You can think about inserting backdoors. You can think about generating adversarial examples that cause bad behavior by the model. You can talk about the fact that sometimes the aggregate information itself might be problematic, right? Like maybe if from the model if the model is like not revealing information that is only revealing public information, maybe that's a problem if it's digesting that public information in a way that's new, right? Like there's sort of lots of things that you could probably figure out about me if you collated everything I've ever written and in one place and thought about it. It's just something that until large language models came along was not feasible to do. OK. So I will stop there for this part of the talk. Shit. And so, so thank you. Let's take a break, and then Lydia and I will confer on using the second part of this morning's block of time. What time should we come back? Should we do 5 past?
Yeah.
All right.
15 minutes.
We added 30 minutes break to the whole day, so now
we're taking it back. Yeah, we were trying to be nice. You asked all these questions.
You're skipping the memorization part.
Yeah, I think I need to get into
That saved you the hassle of
answering your question.